Hi, in the next few videos we're going to look at some geometric annuities. The first one that we're going to look at here is just a standard example. So we got a 20-year annuity with annual payments, has an initial payment of K. Each subsequent payment is 4% more than its preceding payment. The accumulated value of the annuity 1 year after the last payment is $10,000 when using an annual effective interest rate of 7.12%, and we're asked to determine K. So our timeline, we'll capture all this on our timeline, and our timeline looks like this. So we've got first payment of K, next payment increases by 4%, so it's K times 1.04. Next payment is K times 1.04 squared, and so forth, all the way up through the 20 payments. Timelines in years, and the accumulated value is $10,000. I want to just kind of move everything up to get more room. So this is on this next slide, the same timeline, just moved everything up. And I'm looking at an interest rate of 0.0712. Okay, I know that when I'm valuing geometric annuities, I just use this three-step process that we talked about. Step one is to VEP at the valuation date. Value each of the payments at the valuation date. So let's just start with the first payment of K. That payment of K I need to accumulate to get to the valuation date. And if I try to recognize a pattern, and you should see there I need to accumulate that payment of K for 20 years to get to the valuation date. So my value of that first payment of K is K times 1.0712 raised to the 20th power. So I value the first payment of K. I value the next payment of K. The next payment is K times 1.04. I need to accumulate that for 19 periods, so I would multiply that times a 1.0712 to the 19th power. And as I mentioned in the learning video, that's really all you need are those first two terms and how many terms you're going to have in your expression. Well, I'm going to have 20 terms because I've got 20 payments, so I just recognize I've got 20 terms. That's the first step in this three-step process. The second step is to factor out the first term. The first term in that sum there is a K times a 1.0712 raised to the 20th. So I'm going to factor that out. When I factor out that first term, and I get a 1, because when I redistribute, I got to recover what I got when I redistribute. And so I see that the second term in the parentheses, the second term, has got to be a 1.04 divided by a 1.0712, so that when I distribute that K times 1.0712 to the 20th power, I get back to what the second term was in the original expression. So you got to play these games, understand how to factor out the first term, what you're going to get. Okay, so at this point, look at the parentheses, and I see I've got a 1.04 divided by 1.0712 as the second term. I've got 20 terms total. I'm going to recognize, you may or may not do this. You can complete the problem without recognizing this, but I use this 7.12% interest rate for a reason. They do this all the time on these types of problems. I use that because the accumulation factor of 1.0712 is a 1.03 times a 1.04. So when I substitute that back in for the 1.0712, the 1.04s cancel, and I'm left with just a 1 over a 1.03. Again, they do this all the time. So when you see an interest rate like 7.12%, it's there for a reason, because some sort of cancellation like this is likely to happen. Okay, so at this point I've got an expression. I factored out the first term. I'm at step 2. I'm ready to move on to step 3. And in step 3, Step 3 is to recognize the remaining factor, or what's in parentheses there, as either an A double dot or an S. Now I've got angle N, but I see that there are 20 terms, there are 20 payments, so the N is going to be a 20. And because the 1 over a 1.03 is less than 1, I'm thinking of that as a V value. And so I recognize what's in parentheses as an A double dot angle 20. Not only that, but I see the V value as a 1 over 1.03, which tells me that the interest rate that I'm going to be using on the A double dot symbol is a 3% interest rate. In other words, 10,000 would be K times the 1.0712 to the 20th. That's just the first term. And what's in parentheses is nothing more than the VEP expression for an A double dot angle 20 at a 3% interest rate. So at this point, it's just a matter of going to your calculator and using your time value of money buttons, and I get a K value of 164.9. Okay, for the rest of the video, I want to make this comment that if you have the interest rate and you know what the percent increase or decrease in the payments are, for instance, the interest rate is a 0.0712 and the percent increase is a 4%. If you're given all that information, then it's not going to matter generally whether you start your VEP with the first payment or the last payment. We just completed the problem by starting the VEP with the first payment. Let's look at what we would get if we would have done the VEP, the step 1 VEP, starting with the last payment. In that case, that last payment of K times 1.04 to the 19th needs to be accumulated for 1 year. So I would do that by multiplying by 1.0712. So that's what I get as the value of the last payment at the valuation date. The payment immediately before that, which is not shown, would have been a K times a 1.04 to the 18th. And then in order to value that at the valuation date, I need to multiply that or accumulate it 2 years, so multiply it by a 1.0712 squared. And that's the pattern I would get. Again, I only need those first 2 terms and the fact that there are 20 terms total. Now when I go to step 2, I'm going to factor out the first term. Well, the first term in that 20-term expression that's shown is a K times 1.04 to the 19th times a 1.0712. So I'm factoring that out. And what I get when I factor that out is, well, of course, I get a 1 to recover that first term. And then plus, in order to recover the second term, I see that I'm going to need to multiply by a 1.0712 divided by a 1.04. So that, again, when I distribute, check your work by distributing across the parentheses in that last expression and making sure that you recover the original expression for the accumulated value. And I will. So that's the correct expression. That's the correct equation that I have. And now I'm ready to move on into step 3. I'm sorry. Let's go back. This is what it is, and I have to make the same comment. I need to make the same comment that I made before. This is technically what you have. And then I recognize that the 1.0712 is a 1.04 times a 1.03. So when I substitute that in for the 1.0712, the 1.04s cancel, and I'm just left with a 1.03 there. So now I'm ready to move on to the third step, which is to recognize that the term that's in parentheses there, that sum, as the VEP expression, that 20-term sum, recognize it as the VEP expression for an A double dot or an S. Well, because the second term in that sum, it's 1.03, I'm thinking of that's just a 1 plus I. So that 20-term expression is an S, angle 20, using an interest rate of 3%. And so that's the expression that I get for what's in parentheses, that 20-term expression. The equation that I'm solving now is given. I just at this point need to solve the equation for cap K, and I'm going to leave it to you to show, using the TVM buttons on your calculator, do this and show that you're going to get the same value for K that we got before, namely K is a 164.9. Okay, so again, this example was kind of a standard example. When you have both the interest rate, the periodic effective interest rate, and the rate of increase or decrease of the payments, then it usually doesn't matter. It won't matter whether you're starting with the first payment or the last payment on the VEP expressions. Now, when you don't have one of those interest rates, when one of your interest rates is unknown there, either the I or the percent increase or decrease in the payments is unknown, then sometimes it does matter whether you start with the first payment in your VEP expression or you start with the last payment in your VEP expression. So in the next couple of videos, we're going to look at examples just like that. Okay, so I'll see you in the next video.